There is a mathematical threshold where traditional supercomputers simply hit a wall. To solve the hardest physics, chemistry, and cryptography problems, we have to look toward computing systems that operate on the rules of subatomic physics, quantum computing. This diagram outlines the core difference in architecture. Classical computing relies on a simple binary switch, locked into a rigid state of either 0 or 1. A quantum bit, or qubit, represented here by the sphere, breaks that binary constraint entirely. Through a principle called superposition, a single qubit can exist in a blend of 0 and 1 simultaneously. And when multiple qubits are linked together through entanglement, they form a network capable of processing vast webs of possibilities all at once. By calculating multiple outcomes concurrently, these quantum systems slice through incredibly dense mathematical equations in seconds, equations that would take a classical supercomputer millennia to map out. But getting access to that processing power is incredibly difficult. Physical quantum processors are highly experimental, requiring near absolute zero temperatures to function, and time on these machines is scarce and tightly restricted. Even if developers secure access, they must translate abstract quantum mechanics into functional, low-level machine code. It's an exceptionally steep learning curve, requiring advanced physics knowledge just to write basic logic. The combination of restricted physical hardware and highly specialized complex coding creates a massive bottleneck. The theoretical science is proven, but practical software development is struggling to scale. To push the technology forward, developers need a way to cut through the mechanical complexity. They need a high-level tactical command language that allows them to focus purely on mathematical logic, rather than the physics of the hardware itself. That command language is Python. Its highly readable syntax provides a clear, accessible bridge over both the hardware and the coding bottlenecks. Python's clear, beginner-friendly syntax is highly efficient for this kind of theoretical work. It abstracts away the intricate memory management of lower-level languages, allowing researchers to rapidly prototype and iterate complex quantum algorithms. Because of this efficiency, the entire quantum development ecosystem has built specialized frameworks completely reliant on Python's architecture to handle the heavy mathematical lifting. Major technology firms deployed distinct Python modules for this. IBM uses Qiskit for hardware, Google relies on Cirq, and Rigetti provides PyQuil. These frameworks place the heavy artillery of quantum mechanics directly into the hands of classical software developers, using coding structures they already know how to write. Since physical access to quantum processors remains heavily restricted, developers use Python to construct mathematical simulators. These run on standard classical computers, but they precisely mimic quantum behavior. To see how this operates using IBM's Qiskit, developers first import the required libraries and draft a blank single-qubit quantum circuit, represented here as a single horizontal timeline. Next, they apply a mathematical operation called a Hadamard gate. This intentionally forces the qubit out of its rigid binary state and into a fluid state of superposition. To verify the logic, the Python script executes the simulation, firing 1,000 rapid-fire simulated shots through the circuit to gather statistical data. Rather than a single definitive answer, the simulation yields a probabilistic distribution. We see an outcome of roughly 506 zeros and 494 ones. This near 50-50 split is exactly what we expect to measure from a qubit in superposition. It proves the classical simulator is successfully mimicking true quantum randomness. By routing operations through these Python simulators, developers can debug, refine, and perfect highly volatile algorithms entirely offline, ensuring the code works before they deploy it to a physical quantum processor. Quantum machine learning, or QML, integrates classical artificial intelligence with quantum processing, using Python as the primary conduit for the two systems. In these systems, Python acts as a high-speed communications bridge. It takes the output from complex, chaotic quantum logic and routes that data directly into stable classical AI models. Developers accomplish this using specialized quantum libraries like PennyLane, designed to work smoothly alongside standard Python AI tools like TensorFlow and PyTorch. This integration establishes a hybrid workflow. It enables software engineers to experiment with existing machine learning models and selectively upgrade them with quantum enhancements. There is a known vulnerability in relying so heavily on Python. Its raw execution speed is inherently slower than low-level classical programming languages like C++. However, in the highly volatile realm of early-stage quantum research,
pure execution speed is not the primary metric for success. The ability to quickly draft code, test a mathematical hypothesis, and iterate on a complex algorithm is vastly more valuable right now. Python's massive ecosystem of library support and its human-readable syntax prioritize development speed over execution time, making it the primary tool for quantum prototyping. As quantum hardware matures, scales up, and becomes widely accessible, Python's role in this ecosystem will continue to expand. Classical and quantum architectures will function as a synchronized, high-speed engine, with both systems handling the tasks they are best suited for. By serving as the permanent bridge between abstract theory, local simulation, and real-world hardware execution, Python provides the instructions that will drive these new levels of processing power.